Good evening, everyone.
Good evening, sir.
So, is my slide visible?
Yes, sir.
Okay, thank you. So, let's wait for another 5 minutes. Let's see. More students join. I think my pointer is also visible to you.
Yes, sir.
Okay, thank you. Shahbaz, I think you were also present in last class.
Yes, sir. I am present, sir.
Okay. So, what are you doing?
I am doing PhD in
Your sound is Shahbaz, your sound is breaking actually. I'm sorry, Shahbaz, your sound is breaking. Maybe you should check your internet connection actually. Yeah.
PhD. Hello.
Yeah. Now I can hear you. Earlier your sound was breaking. I was not able to hear anything. Hello. Hello. Shahbaz, am I audible? Hello.
Sir. Sir.
Yeah, am I
Thermal
audible?
engineering. Hello, sir.
Yeah, I can hear you now. Yeah.
Hello.
Yeah, I can hear you.
Yes, sir. I am audible, sir. Your sound is coming, sir. Yes, sir. Yes, sir. You are audible.
Okay. I think your sound is having some issue actually. Yeah. Actually, I was not able to hear your introduction. So I think you are doing PhD from where and in which topic? Please repeat.
Yes, sir. Net. Sir, I am. Sir, still first year I joined, sir. Recently I joined, sir. July batch, sir. NIT Andhra Pradesh, sir.
Okay.
Hello,
NIT
sir.
Andhra Pradesh. Yeah. I can hear you now.
Yes, sir.
Okay. So your background is from mechanical engineering.
Yes, sir. Mechanical engineering. Yes, sir.
Okay. And you are also doing PhD in mechanical engineering.
Yes, sir. Mechanical engineering.
Yeah. Nice. So you are doing this course as a part of your coursework or like some extra course?
No, sir. It is in my PhD one subject. We have to take two NPTEL courses.
Okay. So it's your part of coursework, I think then.
Yes, sir. Part of course or curriculum, sir.
Okay, okay, okay. So is it compulsory to attend the course or like what?
Yes, sir. Compulsory to attend the course, sir. Mandatory.
Mandatory. Okay, okay. And the course choices depend on you or your research topic.
Depend upon me, sir. We can choose any course.
Okay, you can choose any course. Okay, okay,
Yes, sir.
okay, okay. I think we have waited enough. So let's start with the today's class. So
Okay,
good
sir.
evening, everyone.
Good evening, sir.
I welcome you all to the live session number 5 for the NPTEL course Energy Conservation and Waste Heat Recovery from the course instructor Professor Pratap Kumar Das and Professor A. Bhattacharya from IIT Kharagpur. I am his teaching assistant Amit Kumar Sharma. So, like you all know, every week on Friday from 9 to 5, we are having a live session in which we discuss some sample problems based on the previous week classes. So these questions are going to help you in your future assignments, and maybe it will be very helpful to you to understand the concept behind the questions. So these live session are interactive session. So in this we have sample questions and we interact with each other and we also discuss some concept and all. So I hope you will learn from this session and it will be going to very helpful in your assignments. Okay, let's start with the class. Okay, so the first question is that identify the correct statements for the figure 1 given below. So we have given a figure in which there is A and B. So you have to identify the correct statements. So statement 1 is the process 1 to 2 in figure A and B show wet and dry expansion respectively in the turbine of organic Rankine cycle. So you have to see the process 1 to 2 and identify are they have shown wet and dry expansion or not. B is the process 1 to 2 in figure A and B show dry and wet expansion respectively in the turbine of organic Rankine cycle. So now it's interchange. Earlier it was wet and dry. Now it's showing dry and wet. The third is superheating is required for the fluid in figure A for dry expansion in turbine, and D is superheating is required for the fluid in figure B for dry expansion in the turbine. So take 2 minutes and try to go through all the options and figures and try to recall the class notes, and based on those try to answer it. So it's quite simple if you closely look at the diagrams. So we have also mentioned in the diagram that one portion is for the saturated liquid and other is for the saturated vapor. So also the regions are marked vapor plus liquid. So basically the wet region and outside the saturated vapor region is the dry region. So maybe based on that, you can identify the correct answer or correct statements. So if you look at this area, it's mentioned vapor and liquid. So basically, this is wet region. Here also, it's vapor plus liquid. It means it's wet region. It is so showing that saturated liquid. So this line is separating. Above this line, completely liquid, and if you see behind this line, there will be vapor plus liquid. At this point, it's showing us the saturated vapor. So beyond this point, there is completely vapor. So okay, so the first statement is saying that the process 1 to 2. So 1 to 2 or 1 to 2. In figure A and B, so this is figure A, is show wet and dry expansion. So yeah, we can see that your temperature is decreasing from T1 to T2 in both. So it's expansion. Pressure is also decreasing. So if you can see here that at T1, you are at saturated vapor condition and you are going to T2 at point 2, 1 to 2. So this 2 point is in the region of vapor plus liquid. Okay. So this 2 point is in vapor plus liquid region. So basically earlier you was at completely vapor state. Now you are going to the vapor plus liquid region. So it will be called wet expansion. Here you can see that at 1 you were at saturated vapor condition and you're going to 2, and 2 point is above the saturated vapor line. So it will be in superheated state. Okay. So it will be dry. So the condition at point 2 will be completely dry. There will be no moisture. Okay. So statement 1 is seems correct. The process 1 to 2, figure A and B show wet and dry expansion respectively in the turbine of organic Rankine cycle. Now if the statement 1 is correct, then obviously statement 2 is incorrect, because in statement 2 it is mentioned that A shows the dry and B shows the wet. It's not the case, so B is incorrect. The C is superheating is required for the fluid in figure A for dry expansion in the turbine. So if we are going for dry expansion in this turbine, then how we can do that? So if we do some superheating, okay, so this one point will be shifted towards this side. So and then if we expand it, then it will going to be the in the dry region. So if we do the superheating, then it is possible for dry to do dry expansion for figure A. So I think statement C also seems correct. The statement D, superheating is required for the fluid in figure B for dry expansion in the turbine. No, because figure B is always in the dry expansion and always is in the superheating region. So it is not required here. So correct answers will be A and C. Is it clear? Okay, I think it's clear. So question number 2. Identify the correct statements for Kalina cycles. So these are some different cycle. Kalina cycle is like quite different. Okay. It is, I think, if you have taken the classes, then you can know. These are for heat recovery at low temperatures. Okay. And slightly different than the Rankine cycle. So what are the correct statement for Kalina cycle? The statement A is phase change process are modified to reduce irreversibility. Fluid circulated is 2 to 3 times of that in organic cycle for the same power generation. It requires only 4 equipment, namely vapor generator, turbine, absorber, and pump. Boiling and condensation of mixture take place at a constant temperature. Take 2 minutes, go through all the points. Do we have any answers? So Shahbaz, are you having any answer?
No, sir.
Okay. So basically, Kalina cycle is a thermodynamic process for converting thermal energy into usable mechanical power. So as compared to the other cycle, in Kalina cycle, we use two fluids with different boiling points. Okay, for it's as a working fluid. So normally, like in working fluid, we are using suppose only single fluid, but here we are using two fluids. Normally, we use H2O and NH3. So generally, we use water and ammonia mixture. Okay, so these are having different boiling points. So based on that, uh, they are going to behave differently as compared to the Rankine cycle. So you know that if suppose let's start with point D. So D saying that boiling and condensation of mixture takes place at constant temperature. So if you know the TS diagram, okay, for Rankine cycle, then you know that my drawing is not so good. Okay, so okay, so you can see the heating, the temperature is constant because at suppose point 1 to 2 there is phase change. Okay, and similarly in condensation from you can say 4 to 5 again the temperature is constant, only phase change is occurring. From 1 to 2 it's going from liquid to vapor, and 4 to 5 from vapor to liquid. So this is the case of a normal Rankine cycle. But in this case, in Kalina cycle, we are not only using liquid, okay? We are not only using the H2O, we are using the combination of H2O plus NH3. So it is like different, okay? The diagram will be like slightly different, okay? It like this, okay? So this 4 comes now here, and this 2 comes to here. So you can see the difference. So it's not straight, okay? So it's not happening at constant temperature. Temperature is changing. So the point D is wrong because in Kalina cycle, the condensation and the boiling does not take place at a constant temperature. Why this is happening? Because if we are only using the H2O, so H2O is having a fixed temperature for phase change. So that's why the temperature is constant for phase change. But if we are using the combination of H2O and NH3, so they are having different boiling points and different conditions, so that the temperature profile is varying. The C is it requires only 4 equipment, namely vapor generator, turbine, absorber, and pump. So this is not the case. It requires some more components. We will see in our further uh, questions, and you can also remember the class notes, okay? Because we need to maintain the purity of NH3. So we need an additional separator. So that separates the like H2O and NH3 and maintain the concentration of NH3. So C is also wrong. A fluid circulated is 2 to 3 times that in organic cycle for the same power generation. No, it is not the case. Fluid is not is 2 to 3 times of the organic Rankine cycle. It is also not the case. It is also wrong. Now the point A is phase change process are modified to reduce irreversibilities. So it's correct. So you can see the phase change, because the phase change is happening because we are using H2 plus NH3. So phase change is like little bit modified. Okay. So and in this way we can extract more heat from the topping cycle, and we can reduce the irreversibility, because we are destroying a very less amount of energy as compared to other cycles. So this A is correct. So the correct answer is option A. So the correct statement for Calvin cycle is that the phase change process are modified to reduce irreversibility. Okay, let's come to the question number 3. So to improve heat exchangers between a gas and liquid stream in a heat exchanger, it is decided to use fins. Okay, so we are going to use fins for heat exchanger. So we are using two types of fluid. One is gas and one is liquid. So select the suitable options. Okay. So option A is fins are generally attached on gas side. B, fins are generally attached on liquid side. C, fins are generally attached on both sides. And D, to improve the rate of heat transfer, addition of fins is not a good decision. So take 2 minutes and try to answer it. So do we have any response? The question is that to improve the heat exchangers between a gas and liquid stream. So suppose there's a heat exchanger, okay. So there is a, suppose the liquid is flowing inside and the gas is flowing outside. Then we want to attach fins. So at which side we should attach the fin and why? Any thoughts, Sabaz?
Sir, fins are on both sides, generally attached on both sides.
Okay. Okay, think more about it because one is liquid and one is gas. Can you give me a practical example of fins? Have you seen them?
Yes, sir, on motors, electric motors on fins and two-wheeler bike.
Yeah. So they are also having fins. So which side they are facing? Fins, which side they are facing?
Airs are to the air, gas side.
To, to the gas side. To the gas side. Okay. So are they having fin inside also?
No, sir.
No. So I think you are saying that the fins are generally attached on gas side then. Option A, I think.
Yes, sir.
So what about option C? What do you think? And what is the reason for this? I'm just giving you a hint. Try to recall the heat transfer coefficient for liquid and gas. Try to recall that. Do you have any rough idea about the heat transfer coefficient of liquid and gases? Like for which it going to be more?
For liquid, it is more, sir.
For liquid it is more. Okay. So
More,
if the heat transfer coefficient is more, then what is the meaning of that?
more heat is going to transfer some more energy gain is going to take place by the
Yeah,
another
yeah,
liquid.
yeah. So for liquid, if the heat transfer coefficient is more, then it is easy to transfer heat from the liquid. But you can see in the gas side, the heat transfer coefficient is low. So,
Low, sir.
but we want to increase the heat transfer. Then what we can do? Then
We add fins, sir.
fins. So fins, what are doing? What is the reason for fins to attach?
Reduce heat transfer.
No, increasing the heat transfer. Increasing the heat transfer. So how the fins are increasing the heat transfer? Any idea what they are doing? Like
Area
you,
of
I think,
contact is more.
yeah, correct. So you have seen like fins like this.
Yes, sir.
So suppose earlier the area was like this straight. Okay, now
Yes, sir.
this. So if you measure the perimeter, you can easily say that this area is very high. Okay, so area A is very high as compared to area B. So now if the gas is flowing, so gas is going from here. Okay, so they are having more area for the heat transfer. So in this way, we can get more heat exchanged. So to improve heat exchange, fins are generally attached on gas side because the heat transfer coefficient on the gas side is small. So I think it's clear. Okay. So Sahbaz, uh, try to participate in discussion because it's good because you can see that in this question, uh, I think it's good to discuss. Okay. So question number 4 is, what is your
Yes, sir.
correct statement regarding organic Rankine cycle? So you have to find out the correct statement or statements regarding organic Rankine cycle. So is to avoid liquid condensation during expansion, it required dry expansion. In this cycle, dry expansion is not required. Low temperature and renewable energy sources can be used for vapor generation. It can run without superheating of the working fluid. So try to recall about the organic Rankine cycle. Any idea? Any guess?
Low temperature.
Sorry?
D is right, sir.
B. Okay, B is right. In the cycle, dry expansion is not required. Okay.
Yes.
Okay, and what about other statements? Maybe because it is mentioned that statement or statements, maybe more than one statements are correct.
I don't have idea, sir.
Okay, okay. So let's see. So the correct options are A, B, and D. Okay. So A, C, and D are correct. So A is to avoid liquid condensation during expansion. It is requires dry expansion. So the dry expansion is the must for organic Rankine cycle. Okay. Because to avoid liquid condensation during expansion. So if the A is correct, then B is automatically wrong. C is that low temperature and renewable energy sources can be used for vapor generation because in organic Rankine cycle, we can use some other fluid except from water, because water requires high amount of heat to convert into vapor. So instead of water, we can use some other fluid that can be converted into vapor at low temperature. So we can use low temperature and renewable energy sources can be used for vapor generation. It can run without superheating of the working fluid. So it can also run without superheating of the working fluid. Okay. So option A, B, and D are correct. So let's come to the question number 5. Which of the following statements are correct or is correct for distillation condensation subsystem DCSS? So it is distillation condensation subsystem of a Kalina cycle with water ammonia as the working fluid. We have given a diagram, we have given a figure. So you have to identify the correct statements for this DCSS. The statement A is basic solution fed to the absorber in the combination of lean solution of NH3 coming from separator and mixture coming from the recuperator. The B is basic solution is needed to raise the temperature for condensation in the absorber. The C is combination of enriched vapor and basic solution is fed to the condenser and no pump is required in DCSS. Go through all the 4 statements, take 2-3 minutes and try to answer this. Sorry. So do you have any answer?
Option A is right, sir.
Option A is right. Okay, so basic solution fed to the absorber is the combination of lean
It's a
solution of
combination
NS3 coming from separator
coming
and
from a
mixture.
separate.
Yeah, yeah, correct. Okay, so option A seems correct to me also. Okay. Any other option?
C, sir. Combination of enriched vapor and basic solution is fed to the condenser.
Okay. Combination of enriched vapor and basic solution is fed to condenser. Okay, it also seems correct to me. Any other option?
Sir, option D is wrong, sir.
Option D is wrong. No pump is required because you can see there is a one pump. Okay, so I think pump is required. Okay, option D is wrong. So it seems that A, B, C both are all three are correct. So yeah, correct answer is A, B, and C. And for detailed solution, you can refer the lecture number 27, time 21:00, or the slide number 5, week 5, handwritten notes. Okay. So basically, the basic solution fed to the absorber. So you can see the absorber is here. So it is a combination of lean solution of NS3 coming from separator. So from separator, some lean solution is coming that is going to the absorber, and the mixture coming out from the recuperator. So from the recuperator, some mixture is coming out that is also going to the absorber. You can see from here. Okay, so these from these two, you can see that option 1 is A is correct. The B is basic solution is needed to raise the temperature for condensation in absorber. So we need some basic solution to increase the temperature. Okay, to raise the temperature for condensation in the absorber. So we need some basic solution to raise the temperature for the condensation in absorber. It is also correct. So that is coming from here. The C is combination of enriched vapor and basic solution is fed to the condenser. So the condenser is here. So you can see that the combination of enriched vapor and basic solution is fed to the condenser. So yeah, it's also correct. So option A, B, and C are correct. If you want detailed solution, you can refer the class video. Let's come to the question number 6. For a trilateral flash cycle, the correct options are. So we have given a trilateral flash cycle. We need to choose the correct options. So try to focus on the TS diagram. I think from the TS diagram you can find the solution. So Saibaz, are you in touch with other students of this class?
No, sir.
Okay. Because normally I think we are having 10 to 12 students in every class from past 4 weeks. Today I think only
Okay.
you have joined. So try to go through the options. It's a trilateral flash cycle. Okay, let's start the solution. So the option A is expansion takes place within two phase region. So yeah, it's correct because you can see that 1 to 2 both are in the two phase region. So this is the expansion. So from the diagram itself, you can identify the expansion, you can identify the points, you can identify the region. So you can say the option A is correct. So expansion takes place within two phase region. The condensation takes place over a temperature range. So check the condensation. So 2 to 3 is the condensation. So is it happening over a temperature range or a fixed temperature? So we can see that 2 to 3 is a straight line. So the temperature is going to be T is constant. So it is not happening at a temperature range. So this seems wrong. The working fluid has a low boiling point. The working fluid has a low boiling point. So yeah, because you can see that with a slow heat transfer, it's changed to the vapor state. Okay, so working fluid has a low boiling point, and with the less amount of heat only, it can again convert it to water. So it also seems correct, or you can say liquid state, not water, in liquid state. The D is substantial amount of heat is transferred to the working fluid in subcooled condition. So yeah, in the subcooled condition, you can see that the substantial amount of heat is transferred to the working fluid. Okay, you can see the heating stream here is coming down and it is transferred a substantial amount of heat that at point 1 the expansion can be started. Okay, so option D also seems correct. So correct answers are A, B and D. And please refer to the lecture number 28 at the rate 20.00. Okay, at 20 minutes of video. So for more detail, you can refer the lecture number 28 video. Let's come to the next question. So in a counterflow heat exchanger, the hot fluid is cooled from 120 to 90 centigrade by a cold fluid which gets heated from 40 to 70 centigrade. 40 centigrade to 70 centigrade, and is a counterflow heat exchanger. Okay, so one is flowing right side, then the other one is flowing left side. The logarithmic mean temperature difference LMTD for the heat exchanger is, you have to find the LMTD.
Option C, sir.
Option C, 50. Okay, let's wait for one more minute. Have you calculated it?
Yes, sir. 54
Okay,
degrees centigrade and
50?
4.
Okay, so nearest is 50.
Yes, sir.
Okay, let's see. So the correct answer is C, 50 degree. So as the temperature difference at two ends of the counterflow heat exchanger are same, so because you can see the difference, 90 minus 40 will be 50, and 20, even 20 minus 70 is also 50. So when the temperature difference at both the ends are same, then that the temperature difference become the LMTD. Okay, so LMTD is 50 only, not 54. Okay, so the LMTD is 50 degree only because the temperature difference at the terminal ends are similar. So it becomes the LMTD. As the temperature difference at two ends of the counterflow heat exchanger are same, the temperature difference should be same throughout the length of the heat exchanger, and it is the LMTD. The correct option is C. Is it clear?
Yes, sir.
Okay. Okay. So the more detailed solution is also here. We can see that if you apply the formula for LMTD, let's see. So mathematically, we can show it like this, that LMTD is del T1 minus del T2 upon ln T1 upon T2. So here a special case of counterflow heat exchanger is arising as del T1 equals to del T2 equals to del T, because we know that if del T1 cancel out, it will become 1, and value of ln1 is equals to 0, and 1 upon 0 is tending to infinity. Okay, so in this case, this value is going to become 0 and the whole value is going to become infinity. Basically, the delta Tm is going to infinity. So we cannot say the infinity is the LMTD. So what we will do, because you can say, and also the T1 minus T2 is also 0. So it is form of 0 by 0. So this is undefinable, this is indeterminate value. So we can apply the L-Hospital rule. So apply the L-Hospital rule. By applying the L-Hospital rule and by solving, we will get that LMTD is become delta T only. Okay, so in this way, this statement is correct. So you can maybe remember it, or you can mathematically prove it. So the LMTD will be 50 degree centigrade. It's quite an important question. Okay, is it clear? I think it's clear.
Yes, sir.
Question number 8. Identify the correct expression of NTU, net heat transfer unit, in a heat exchanger. So all symbols have their usual meanings. So what is the correct expression to represent the NTU?
First option, sir.
Option A.
Option A.
Okay, let's wait for 1 more minute. Okay, so the correct option is A only, because the NTU is UA, where U is the, what is the U? What is the U?
Overall
What
heat
is the,
transfer coefficient.
yeah, U is the overall heat transfer coefficient, and the A is the area. Okay, and C is the heat capacity, C minimum heat capacity. Okay, so it's important that we have to take the minimum one, C minimum. NTU is UA upon C minimum. So the correct option is A. So a counterflow concentric tube heat exchanger is used to cool the lubricating oil for a large industrial gas turbine engine. The flow rate of cooling water through the inner tube is 0.2 kg per second, while the flow rate of oil through the counter annulus is 0.1 kg per second. The oil and water enter at a temperature of 100 degrees centigrade and 30 degrees centigrade respectively. What will be the outlet temperature of water if outlet temperature of the oil is to be 60 degrees centigrade? Specify heat of oil and water are Specific heat of oil and water are 2131 joule per kg Kelvin and 4178 joule per kg Kelvin respectively. First of all, you can see the question is quite large. So go through the question very carefully and slowly and try to note down the points and start the solution. Take 2-3 minutes. Take care of units. Shahbaz, are you getting any answer?
Sir, C, sir.
Option C. Okay, let's see. So no, option C is wrong. The correct option is option A. So let's see the solution. So first of all, find out the heat transfer Q. So Q will be mc delta T. So you can see we have given the specific heat of oil, the temperature of oil, and the flow rate. So put all the values. So Q will be 8524 watt. Okay. Since the heat transfer rate remain the same, because heat transfer rate will remain the same, this Q will remain same. Using the heat transfer relation for the cooling water, one gets the outer temperature of water. So we can put the value of Q and put the formula for water mc again delta T. So we know the inlet water temperature. Okay. So in that we can find the outlet temperature also. So you can see, I think we have given the water entry temperature we know at 30 degree. So we can know the outlet temperature from this equation. So put the value of Q here and put the value of M, C and the known temperature and solve it. You will get the temperature is 40.2 degrees centigrade. So the correct option will be option A. So basically, because we know that in heat exchanger, the heat is remain same. Q will remain same. Okay. So it will be Q of oil equals to Q water. So this Q is given by the oil and this Q is received by the water. Okay. So it is remain same. We are not considering any effectiveness and all. We are considering fully efficient conditions. Okay. So this completely Q that has been given by the hot fluid is directly go to the cold fluid. In this way, by equating, we can find out the temperature. Is it clear? Okay, I think it's clear. So in the previous question, what is the LMTD of heat exchanger? So I think you know all the temperatures. Okay, so now find the LMTD. What will be the LMTD for this question? Now you know all the temperatures and everything. So these are the options: 38.2, 43.2, 53.9, 50.5.
B, sir. Option B,
Option
sir.
option B.
B.
Oh, very good. It's correct. So the correct answer is option B. Because we have calculated the all the temperature, all the four temperatures. Now just we have to put the temperatures in the formula of LMTD. So by putting it, we will get 59.8 minus 30 upon ln 59.8 upon 30. It's going to be 43.2 degrees centigrade. So correct option is option B. So question number 11. In a cogeneration plant with a pass-out turbine, the rate of steam extraction of process heating is uh, omega 1901.4 kg per hour. The TS diagram of the plant is shown below. The enthalpy values at different locations corresponding to omega is given. The boiler capacity in kg per hour. So you have given so much of values. So try to first uh, see the figure very carefully. Okay, and mark the important point. Maybe you can try the mass balance or heat balance. You will get the answer. So normally in these types of question, the main thing that question is quite long, the figure is quite complicated. Okay, that's why we just have a fear in our mind, but in actual, the solution is very simple. So try to just focus on the important part of the figure that is going to be useful for you. Are you trying, Shahbaz?
Yes, sir.
Okay. Okay, let's see the solution. Are you having any answer?
No, sir.
Okay. So okay, let's see the question number 11. For detailed solution, you can refer to the video lecture number 28. And the solution is that omega h7 plus omega s minus omega h5 equals to omega s h8. Okay, so where is the omega 8 point? So this is the point 8 and this is the point 7 and this is the point 5. Okay, so you can see that that omega 7 into omega. So omega 7 into omega plus omega 5 h5 into omega s minus 5. So this stream is going here, this stream is going here, they are coming to merging at point 8. So this is this is. So you have to just basically you can say we are applying the energy balance at this point. So how much energy is coming and how much is going? We just applying this. So we know the values of we have given. We know the omega values. So just put the values. You will know the answer. So you can see the diagram seems very complicated, but the only concern is should be this point. Okay. So I think it's easy, very easy, only 3-line solution. But initially it seems very difficult. So always try to remember this thing that focus on the points which are going to be important. Focus on those points and try to apply basic equations. Use basic equation and you will get the answer. Okay. Question number 12. So hot exhaust gases which enters a finned tube cross flow heat exchangers at 300 degrees centigrade and leaves at 100 degrees centigrade are used to heat pressurized water at flow rate of 1 kg per second from 35 degrees centigrade to 125 degrees centigrade. The overall heat transfer coefficient based on the gas side surface is UH 100 watt per meter square Kelvin. Assume specific heat of cold fluid. Okay. The maximum possible heat transfer is. Take 2-3 minutes to find the solution. Bas, any success? Are you getting any answer?
No, sir. How to calculate LMTD for cross flow, sir?
Okay. So I think it's quite so. The main thing is that here, what they're asking you the not LMTD. They're asking the maximum possible heat transfer. The first thing is that. And LMTD, I think the for cross flow also that the formula is same. The point is that the terminal temperature difference little bit changes as compared to the parallel flow. So you can refer the class notes for that. And I think I think we have also seen them in our previous questions. Okay. So here they have asked the maximum possible heat transfer. So for the maximum possible heat transfer, what should be the condition? Because you know that Q is C delta T. So this delta T is the temperature difference, C is the heat capacity. So if you want this Q to be higher, then this delta T should be lower or higher. What do you think? If you want this Q to be higher, so this delta T should be lower or higher. It should be lower or higher. What do you think?
Oh, higher, sir. Delta should be higher.
Delta T should be higher. Because if we want this Q to be higher, then this delta T should be higher. And what about this capacity? It should be lower or higher? Heat capacity. It should be lower. Okay. So this heat capacity should be minimum and the delta T should be maximum. So the maximum temperature difference will occur for the maximum like entering point of the hot fluid and the entering point of the cold fluid. Okay. So TH I minus TCI. So we have given the 335. Now we have to find out the C minimum heat capacity. Okay. So the cold fluid capacity is MC CPC. It is coming to 4197 joule per kg Kelvin. And for high CH is MC MH CPH. So it's coming out to be 1889. So this is minimum. We're going to take this value. So for maximum possible heat transfer, Q max, so it will be C minimum and maximum temperature difference, delta T maximum. So put this value and this delta T, you will get 500 kilowatt. Okay. So this will be the maximum heat transfer. Okay, let's come to the question number 13. For the above problem, determine the effectiveness of heat exchanger. So for this question, sorry, what is the effectiveness of heat exchanger? Let's take 1 to 2 minutes to answer. Options are 0.955, 0.755, 0.455, 1.25. Okay. So the solution is like this. So the actual heat transfer would be the cold capacity, and this is okay. So it's going to be 378 kilowatt. So the actual heat transfer is going to be 378 kilowatt, but the maximum heat transfer that can be uh, done, that is, as we have calculated, is 500 kilowatt. So the effectiveness is Q upon Q max. Q upon Q max. It's going to be 0.755. So this heat exchanger is 75.5% effective. Okay. The formula for effectiveness is actual heat transfer rate to the maximum heat transfer rate. In a counterflow heat exchanger, the product of specific heat and mass flow rate is same for the hot and cold fluids. If NTU is equal to 0.5, then the effectiveness of heat exchanger is. Apply the formula of NTU for the counterflow heat exchanger. Try to remember that. You will find the answer.
C, sir. C.
So you are saying option number C. Okay, let's see. So yeah, it's correct. So as the product of specific heat and mass flow rate is same for the hot and cold fluids, so it's again a special condition. So the effectiveness of heat exchanger is represented by NTU upon 1 plus NTU. So effectiveness is NTU upon 1 plus NTU. Put the value of NTU, which is 0.5. So you will get 0.5 upon 1 plus 0.5, it comes to 0.33. Okay. So hot oil is cooled from 80 degree to 50 degree in an oil cooler, which uses air as the coolant. The air temperature rises from 30 degree to 40 degree centigrade. The designer uses a LMTD value of 26 degree centigrade. Identify the type of heat exchanger. Given hot oil is cooled from 80 degree to 50 degree in an oil cooler, which uses air as the coolant. The air temperature rises from 30 to 40 degree centigrade. The designer uses LMTD of value 26 degree centigrade to identify type of heat exchanger.
Parallel flow, sir.
It's parallel flow. Okay, let wait for, just try to solve or try to one more, you can say, attempt. Okay, so let's see. The solution is like cross flow because we know that the LMTD is del T1 minus del T2 upon ln log ln del T1 upon del T2. So consider parallel flow. So 80, 50, 30, 40. So the theta 1 will be 50 degree, theta 2 will be 10 degree centigrade. So if you put all the values, it will come 24.85 for parallel flow. So for the counter flow, it's 80, 40 and 50, 30. So it comes to be 28.85. Okay. So it is having more temperature difference. So it's going to be the best one. So the best is cross flow heat exchanger. Okay. Because the designer is using the LMTD value of 26. So you can so okay, this 26. So yeah, so because the given were 26 value, okay, so it is between the parallel flow and counter flow. So if we go for parallel flow, it will be 24.85. We will go for counter flow, it should be 28.85, but the value is 26. So it should be between these two values. So it's neither the parallel flow nor the counter flow, it should be the cross flow. So the chosen heat exchanger will be the cross flow heat exchanger. Is it clear?
Yes, sir.
Okay. So identify the correct expression of NTU. I think we have already covered this. This NTU is equal to UA upon C minimum. So select the cycle could be used as a low temperature power cycle. So we have covered like Joule cycles and Otto cycles. They are high temperature cycles. They are maybe mainly used for as a topping cycles. But we are asking for the low temperature power cycle, so that are Kalina cycles and the trilateral flash cycles. So the correct options are B and D. Kalina and the trilateral cycle. Now identify the correct statements for Kalina cycles. So the option A is phase change process are modified to reduce irreversibility, and the NH3H2O mixture is suitable working fluid. Okay, and it requires only 4 equipment throughout the cycle. The composition of NH3 NH2O mixture is uniform. So it's not uniform. We know that D is wrong. D is also wrong because it requires only 4 equipment. No, it also requires uh, a pump separator and the recuperator. Okay, so the option A and B are correct. Phase change process are modified to reduce irreversibilities because in Kalina cycle we are using two types of fluid. So the temperature, the phase change is not happening at a fixed temperature. So we are able to extract more heat from the topping cycle. So we are reducing the irreversibility. Match the cycles with their components. So try to solve this. Don't see the answer directly. Try to explain the reasoning. Sebas, try to think the reasoning for the answer, and I would like to hear from you. Okay, so the correct answer is option B. So the Kalina cycle is requirement. There is requirement of basic solutions. So 1 to 4. Let me mark it. Organic Rankine cycle is require dry expansion. Trilateral phase cycle, it require an expander. The gas power cycle require a combustion chamber because it's operating at high temperature and we need to generate the high temperature, so we need a combustion chamber for burning. Okay. The correct option is option B. In a heat exchanger, the fluid undergo maximum temperature difference that have minimum heat
Sir,
capacity rate.
questions, sir. Slide,
Sorry.
sir, slide is not visible, sir. First question is not changed. Only first question is visible.
Okay, slides are not visible now.
No, sir. Slide first one question is there. You haven't changed the slide questions.
Okay. Let me reshare. I think there is some issue in the network. Let me reshare the slides. Okay.
I will join and again.
Yeah, let me reshare. Let me reshare it. Is it now visible? Question number 1. I am at question number 1.
No, sir. Yes, sir. Question number one is
Okay.
visible, sir.
Now question number 2 is visible.
Yes, sir.
Okay. So I think we have covered, because we have the low temp. We have to select the cycle that could be used as a low temperature cycle. So we know that Joule cycle and Otto cycles are high temperature cycle. So option B and D are correct. Identify the correct statement for Kalina cycles. So the statements are A and D. So because in Kalina cycles, phase change process are modified to reduce irreversibilities. Okay, so we have also discussed it in earlier questions also, because we have because there is more heat transfer as compared to the organic Rankine cycle or Rankine cycle. So we are decreasing the irreversibility, and the NH3H2O mixture is a suitable working fluid. Yeah. Now match the following. So its correct answer was option B. The Kalina cycle is requirement. It's a component of basic solution. The organic Rankine cycle require dry expansion, and the trilateral phase cycle would have an expander, and the gas power cycle is a dry expansion. Sorry, the combustion chamber. Question number 5. In a heat exchanger, the fluid undergoes maximum temperature difference that that have minimum heat capacity rate and maximum temperature difference. I think we have recently covered a numerical on this. Okay. For a fluid to undergo maximum temperature difference, the heat capacity should be minimum and the temperature difference should be maximum.
Sir, previous question.
Yeah, this one. Hello. Sebas, I am not able to hear you. This are you talking about this question?
Sir, this question, yes, sir. Sir, previous fourth question, sir, match the cycles.
Yeah.
Yes, sir, this sir.
PPT will be shared. No, don't worry. PPT will be shared with
Okay.
you. So don't worry. Don't
Okay, sir.
you don't need to write or you just need to learn and try to solve the question. Okay. PPT will be shared with you. So the
Yes, sir.
effectiveness of a counterflow heat exchanger in terms of NTU, if the product of specific heat and mass flow rate is same for the hot and cold fluid. So if the C hot equals to C cold,
Sir, question haven't changed this.
again. So it's question number 6 or 5.
Question.
You are out at which question? Question number 6 or 5?
Uh, uh,
I I
now,
think Sabaz, I think you are having some network issue, I think.
six, sir, six. Correct, sir. Correct. Now I am
Yeah.
following, sir.
Yeah, I think your
Sir, option
network
B,
is
sir.
I think your network is lagging, I think.
Six, sir. Six.
Yeah, okay. So if the product of the
Correct only,
specific
sir.
heat
Sequence.
and mass flow rate is same for hot and cold, then the NTU, the effectiveness is NTU upon 1 plus NTU. I think we have also covered a
Option B,
numerical
sir.
on this.
Correct.
What is the correct statements regarding organic Rankine cycle? So the correct statements are to avoid liquid condensation during expansion, it requires dry expansion. So yeah, it's correct. And it can run without superheating of the working fluid. So these are two statements which are correct. I think we have already discussed this in our previous question segment. I think this question is identify the correct TS diagram of a trilateral place cycle. So we have to find out the correct TS diagram. So as we know, the trilateral it's look like a look like a triangle. So you can say heating, expansion, and condensation. So option A is correct. To improve heat exchange between a gas and a liquid stream in a heat exchanger, it is decided to use fins. Choose the suitable options. So fins are generally located or attached on a gas side. We have covered this already. To analyze the heat exchanger, what are the common assumptions? So whenever we want to analyze the heat exchangers, we should always assume some common assumptions. So those assumptions are like heat loss to and from surroundings are assumed to be negligible. So we are not considering heat loss to and from surroundings. And the temperature of each fluid is assumed to be uniform at the cross section. So these two are the common assumption. Identify the correct statements for the process 1 to 2 in the figures given below for organic Rankine cycle. So it is shown weight expansion and it shows isentropic expansion because you can see this is the water plus vapor region, and you can see it is 1 to 2, it's completely straight, it is isentropic. Okay, so the answer is B and C. Hot oil is cooled from 80 degree to 50 degree in an oil cooler which uses air as the coolant. The temperature rises from 30 to 40 degree. The designer used LMTD value of 26 degree. I think we have just already solved this question. It is cross flow. So you can try this one. Hot fluid intersect in a cross flow heat exchanger at 300 degrees centigrade and leaves at 90 degrees centigrade. I think we have also completed this one. Okay, I think so. We have given U, we have given area, and you have to find out the NTU. So you have given the U, area A. Okay, so you have given the specific heat capacity of cold fluid. Okay, so maybe you need to find out the LMTD. After that, you can apply the formula of NTU, and the answer will be 0.31. So I think these questions can be tried at home. Okay, so any doubt in today's class?
No doubt, sir.
Okay, so we are still having 5 minutes left. So I think today we have covered about the different cycles and heat exchangers and low temperature cycles and about heat exchangers. Okay, I hope these questions are clear to you and these are going to be very helpful for you in your assignment solutions. And the video of this live session and this PPT will be shared with you from the NPTEL team. So maybe those who are unable to attend today, they can see the video and they can see the slides to understand more about this question and solutions. Okay, so let's wait for 5 more minutes. If anybody have any questions, we can wait and we can take for that. So if you have any doubts, Shahbaz, you can ask me if you are having any doubt regarding this course or subject. If you want to ask anything about PhD, you can ask.
No doubt, sir.
Very nice. So I'm still available for 5 minutes. So if anything wants to ask anything, floor is open for you.
Sir, are you a faculty, sir, or teach?
Actually, I am also pursuing my PhD. I am about to complete my third year, and I am
Okay, sir.
pursuing my PhD at IIT Delhi. And currently, I am working as a visiting researcher at TU Delft, Netherlands, as a part of my PhD work. So
Okay, sir.
for almost 1 year, I will be in TU Delft, and after that, I will go to again IIT Delhi and complete my PhD.
Okay, sir.
So from where did you completed your master's?
NIT Andhra Pradesh, sir.
Okay, same college. Okay.
Same college, sir.
So on which area you were working?
Thermal engineering, sir. Thermal.
Thermal is like quite broad. On which specific area you were working?
Thermal energy storage system, sir.
Okay, thermal energy storage system. Okay.
Yes, sir. Sir, you are from
So
your research has been on which side?
yeah, I am working on high temperature fuel cells.
High temperature fuel, sir. Okay, sir.
Yeah. So you are basically storing the energy. Okay.
Yes, sir.
So
Still,
how are
still
you?
not the work has been started, sir.
Okay, okay.
Still, I am learning this research paper, sir. Still, the work has been not started. Just that sir has told me go through these topics and
Okay,
then research
okay.
papers.
No, no, I
First,
am asking about
1 month
your
has.
I am asking about your MTech actually. In MTech, I think you have completed some work, some project or what?
Projects and MATLAB coding on MATLAB I have done from DRDL internship project I have done
Okay,
there, sir.
okay, okay,
Hyderabad
okay.
DRDL.
Okay, nice, nice. So in MTech, you were doing some modeling part, and now you are doing both modeling and experiment, I think.
Yes, sir. Then
Right.
still not the work has been started. Modeling work, sir, and simulation work.
Simulation work. Okay, okay. Okay then. Uh, nice to talk with Sehbaz and nice to meet you everyone. Okay.
Yes,
I
sir.
hope next time also on Friday, next Friday, you will be here to join the session. So I
Okay,
think
sir.
it's uh, it's complete for today. Okay. So I'm ending my
Yes, sir.
PPT.
Okay, sir.
So okay. Thank you everyone for joining and thank you. Thank you.
Thank